NEC table 430.52 is used for determining the maximum rating or setting of motor branch circuit, short circuit, and ground fault protective devices. This table provides multipliers for different types of protective devices, such as inverse time circuit breakers and fuses. The question revolves around the application of exception number 2 of 430.52C3 when sizing a circuit breaker for motors with a full load amperage, or FLA, of 8 amps or less. Typically, to size a breaker, you would use the percentages listed in table 430.52. For example, if using an inverse timed circuit breaker, you might multiply the motor's FLA by 250% as described in the question, and then select the next highest standard breaker size if the calculated value doesn't match a standard breaker size. The exception number 2 of 430.52C3 provides an alternative approach for smaller motors. Specifically, if the motor FLA is 8 amps or less, you are permitted to use a 15 amp circuit breaker. This exception is provided to simplify installations where very small motors are used, and the standard calculation would result in a breaker size smaller than the commonly available minimum breaker size, which is 15 amps. In the scenario described, there are two motors, one with a 6.8 amp FLA and another with a 2.2 amp FLA. If you were to apply the 250% rule, you would calculate 6.8 amps times 2.50, resulting in 17 amps. According to standard practices, you would choose the next low breaker size, in this case, likely a 15 amp breaker. For the 1/2 horsepower motor with a 2.2 amp FLA, the calculation would be 2.2 amps times 2.50, resulting in 5.5 amps. Following standard practices without the exception, you would choose a 5 amp breaker or possibly the next available standard size. However, since both motors have an FLA of 8 amps or less, exception number 2 of 430.52C3 allows the use of a 15 amp circuit breaker for both motors. It is important to understand that this exception overrides the standard 250% rule when the motor FLA meets the specified criteria. The rule aims to simplify the selection process and allow for the use of a commonly available breaker size. A 15 amp breaker is generally considered the minimum standard size for circuit breakers. This means that you are unlikely to find breakers with lower amperage ratings readily available for typical residential or commercial applications. Exception number 2 of 430.52C3 addresses this issue by permitting the use of a 15 amp breaker when the standard calculation would result in a smaller, less common size. In summary, if a motor has an FLA of 8 amps or less, exception number 2 of 430.52C3 allows for the use of a 15 amp circuit breaker, regardless of the outcome of the 250% calculation. This exception is in place to accommodate smaller motors and simplify the breaker selection process. It is always important to consult the latest edition of the NEC and any local amendments to ensure compliance with all applicable codes and regulations. The application of NEC 430.52 and its exceptions requires a careful understanding of motor characteristics and protective device ratings. Consulting with a qualified electrician or electrical engineer is always recommended for complex or critical applications. Remember that while exception number 2 of 430.52C3 permits the use of a 15 amp breaker for motors with an FLA of 8 amps or less, it is crucial to ensure that the selected breaker provides adequate protection for the motor and circuit wiring. The breaker should be sized to protect against short circuits and ground faults while allowing the motor to start and run without nuisance stripping. In addition to the breaker sizing, it is also important to consider the wire size for the motor branch circuit. The wire must be sized to carry the motor's full load current plus any applicable directing factors or adjustments for ambient temperature or conduit fill. NEC Table 310.15b16 provides ampacity ratings for various wire sizes and insulation types. When selecting the wire size, it is essential to ensure that the wire ampacity is sufficient to handle the motor's full load current and any other loads connected to the circuit. It is also important to consider the voltage drop in the circuit, particularly for long runs. Excessive voltage drop can cause the motor to operate inefficiently or even fail. NEC 430.52 provides guidance on voltage drop limitations for branch circuits. Proper grounding is another critical aspect of motor installations. The grounding system must be designed to provide a low impedance path for fault current to return to the source, minimizing the risk of electric shock. NEC 250 provides detailed requirements for grounding and bonding electrical systems. In addition to the NEC requirements, it is important to consider any local codes or regulations that may apply to motor installations. Local codes may have more stringent requirements than the NEC, so it is always best to check with the local authority having jurisdiction. Motor control circuits also require proper protection. Control circuits typically operate at lower voltages than the motor power circuit, but they can still pose a risk of short circuits or overloads. Control circuit transformers should be protected with overcurrent devices on both the primary and secondary sides. Control circuit wiring should also be sized and protected in accordance with NEC requirements. When installing motors in hazardous locations, special precautions must be taken to prevent explosions or fires. Hazardous locations are classified based on the type and concentration of flammable materials present. NEC Articles 500 through 516 provide detailed requirements for electrical equipment and wiring in hazardous locations. It is essential to use equipment that is specifically listed and labeled for the class and division of the hazardous location. Regular maintenance is crucial for ensuring the safe and reliable operation of motors. Motors should be inspected periodically for signs of wear or damage. Bearings should be lubricated regularly to prevent overheating and failure. Motor windings should be checked for insulation breakdown. Any damaged or worn parts should be replaced promptly. In addition to the electrical considerations, it is also important to consider the mechanical aspects of motor installations. Motors should be mounted securely to prevent vibration and movement. Motor shafts should be properly aligned with the driven equipment to prevent excessive wear and tear. Motor cooling systems should be kept clean and free of obstructions to ensure adequate cooling. When selecting a motor for a particular application, it is important to consider the motor's horsepower, speed, torque, and duty cycle. The motor should be sized to provide adequate power for the load without being overloaded. The motor's speed should match the speed requirements of the driven equipment. The motor's torque should be sufficient to start and accelerate the load. The motor's duty cycle should be appropriate for the application. For example, a motor that is used for intermittent duty may not be suitable for continuous duty applications. Motor efficiency is another important consideration. High-efficiency motors can save energy and reduce operating costs. The National Electrical Manufacturers Association, or NEMA, has developed standards for motor efficiency. NEMA premium efficiency motors are the most energy-efficient motors available. When replacing an existing motor, it is important to select a replacement motor that is compatible with the existing electrical system and driven equipment. The replacement motor should have the same horsepower, speed, and voltage as the original motor. The replacement motor should also have the same frame size and mounting dimensions as the original motor. When installing a new motor, it is important to follow the manufacturer's instructions carefully. The manufacturer's instructions will provide detailed information on the proper installation, wiring, and maintenance of the motor. It is also important to consult the NEC and any local codes or regulations that may apply to the installation. Motor starting methods can have a significant impact on the performance and reliability of the electrical system. Reduced voltage starting methods, such as autotransformer starting and part winding starting, can reduce the inrush current and voltage drop associated with motor starting. These methods can be particularly useful for large motors or systems with limited capacity. Variable frequency drives, or VFDs, can be used to control the speed and torque of motors. VFD can also improve motor efficiency and reduce energy consumption. VFD are commonly used in applications such as pumps, fans, and conveyors. Power factor correction capacitors can be used to improve the power factor of motor circuits. Power factor is a measure of how efficiently electrical power is being used. A low power factor can result in increased energy consumption and higher utility bills. Power factor correction capacitors can improve the power factor and reduce these costs. Surge protection devices, or SPDs, can be used to protect motors from voltage surges caused by lightning or switching transients. Voltage surges can damage motor windings and other electrical components. SPD can divert these surges away from the motor and protect it from damage. Harmonic filters can be used to reduce harmonic distortion in motor circuits. Harmonics are unwanted frequencies that can cause overheating, equipment malfunction, and reduce system efficiency. Harmonic filters can block these harmonics and improve the overall performance of the electrical system. Motor overload protection is essential for preventing motor damage due to overheating. Overload relays are used to detect excessive current and trip the motor circuit breaker. Overload relays should be sized to protect the motor without causing nuisance tripping. Short circuit protection is required to protect motor circuits from damage due to short circuits. Fuses and circuit breakers are used to provide short circuit protection. Fuses and circuit breakers should be sized to interrupt the fault current before it can cause damage to the motor or wiring. Ground fault protection is required to protect personnel from electric shock due to ground faults. Ground fault circuit interrupters, or GFCIs, are used to detect ground faults and trip the circuit breaker. GFCIs are commonly used in wet locations such as bathrooms and kitchens. Motor control centers, or MCCs, are used to house and control multiple motor circuits. MCC provide a central location for motor starters, overload relays, circuit breakers, and other control devices. MCC can simplify motor control and maintenance. Programmable logic controllers, or PLCs, are used to automate motor control systems. PLC can be programmed to control motor starting, stopping, speed, and other functions. PLC are commonly used in industrial applications. Human-machine interfaces, or HMIs, are used to provide a user interface for motor control systems. HMI can display motor status, alarms, and other information. HMI can also allow operators to control motor functions. Remote monitoring and control systems can be used to monitor and control motors from a remote location. These systems can provide real-time data on motor performance and allow operators to remotely start, stop, and adjust motor settings. Remote monitoring and control systems can improve efficiency and reduce maintenance costs. Energy management systems, or EMSs, can be used to optimize motor energy consumption. EMS can monitor motor energy usage and identify opportunities for energy savings. EMS can also control motor speed and other parameters to reduce energy consumption. Predictive maintenance techniques can be used to predict motor failures and schedule maintenance before failures occur. These techniques can include vibration analysis, infrared thermography, and oil analysis. Predictive maintenance can reduce downtime and extend the life of motors. Commissioning is the process of verifying that a motor and its control system are properly installed, wired, and configured. Commissioning should be performed before the motor is put into service. Commissioning can help to identify and correct any problems before they cause damage or downtime. Training is essential for personnel who install, operate, and maintain motors and motor control systems. Training should cover topics such as motor theory, wiring practices, troubleshooting, and safety procedures. Proper training can help to prevent accidents and ensure the safe and reliable operation of motor systems. Safety is always the top priority when working with motors and motor control systems. Always disconnect power before working on any electrical equipment. Wear appropriate personal protective equipment, such as safety glasses and gloves. Follow all applicable safety procedures. By following these guidelines, you can ensure the safe and reliable operation of motors and motor control systems. Remember to always consult the latest edition of the NEC and any local codes or regulations that may apply to your specific installation. The NEC provides comprehensive requirements for motor installations, including sizing of conductors, overcurrent protection, and grounding. Adhering to these requirements is essential for ensuring the safety and reliability of motor systems.